here at the banquet. The next speaker is somebody I've had the great fortune to be able to work with for more than 25 years now, and it's been an opportunity for me to learn a great number of things, but now I guess we'll find out. I'll get to find out everything else too.
Well, thank you, Eric. So it's a great pleasure and privilege to speak here, and I want to thank the organizers for inviting me, and thank Jack and Misha for running this great institute for 25 years. Let's see, in my, I guess today I want to give a kind of the prequel to romance talk. So it's not going to be as sophisticated as that talk. But I also want to talk about some history. As you get older, it just seems more, this is more what you have to contribute is these stories that you remember. Let's see, in my role as historian, I want to switch to last names, okay? So I'm going to just, so it will be Lubitsch and Milner from now on, okay? So to the extent that I remember. Okay, so the complex Hénon map is approximately 25 years old, as is the IMS. So the Hubbard first started speaking about it in 1986, but the first papers on the subject started appearing a little bit after that. 1989 was the date of a Friedland-Milner paper. 1991, Eric and I wrote our first paper in 1992. Pardon? Oh, Bedford. Yeah, thank you. Bedford. Appreciate it. 1992. Well, I don't want to give away exactly who my friends, are. So 1992, Farnese and Sibony wrote their first paper on the topic. So let me go back to that period. So Hubbard introduced the following map. X squared plus c minus delta y comma x, where we're thinking of f as mapping C2 to C2. Hubbard gave a series of talks on this. So why is it interesting? Well, so f is a diffeomorphism with constant Jacobian equal to delta. If delta equals 0, then this map essentially reduces to the quadratic family. Then f is equivalent to sort of f sub c of z equals z squared plus c. On the other hand, if the parameters delta and c are real, then we can think of f as giving a map from R2 to R2, and this is the classic Hénon map. So this is a well-known character in the world of dynamical systems. It was a place where a setting for the study of strange attractors. So this family interpolates between one variable complex dynamics that Hubbard knew and loved. And yeah, Dennis.
Can You describe it as like a natural construction from the one-dimensional map, like a functorial construction. I mean, you write a formula with it. What is the meaning of it?
Yeah, I'm not. Let's see. So let me draw you a picture here. So if we take a box, what it does is it takes this box and it shears it and maps it across itself, where delta corresponds to this width, so that delta equals 0 corresponds to this kind of picture here. So perhaps it's some more or less canonical fattening of the one-dimensional map. But just to say that it's related to the one-dimensional map, it's more complicated than the one-dimensional map, right? And let's, I want to emphasize that several times. Okay, so Hubbard's ambition was to apply the lessons learned from the study of the quadratic family to this family, in particular to understand sort of perhaps combinatorial structures of individual maps, and as well as combinatorial structures in parameter space. And a key to Hubbard's vision was to use computers to motivate theorems, as happened in the one variable setting. Okay, so in Hubbard's talk, he introduced certain important sets. So let me give you a second cartoon of the picture of the dynamics of the map. If we sketch here absolute value of x and absolute value of y, then the map, there's a kind of filtration here describing the behavior of the map, so that points that move off here tend to go off to infinity in forward time, points here go off to infinity in backward time. So we can, so in particular, the only recurrence can only happen for bounded orbits. So Hubbard introduced sets k plus and k minus. These are the sets of p in C2 such that f to the n of p is bounded as n goes to plus or minus infinity. And k is equal to k plus intersect k minus, which is the set of bounded orbits. Just as in one variable, normal families arguments apply. For example, if you look at the interior of k plus, normal families arguments tell you there can be no expansion in the interior of k plus. So it's interesting to look at those at the boundary of k plus. So we define j plus and j minus to be the boundaries of k plus and k minus. J is equal to j plus intersect j minus. So by construction, any kind of recurrent hyperbolic or expansive behavior must occur inside this set J. Okay. If we, again, let me just draw another schematic of this is a sort of a schematic of a parameter value that Hubbard described in his talks in 1986. But in this picture, so let's assume for this purposes of this talk, assume that delta is less than 1. So our map is dissipative. So in this case, there is no interior to k minus. So in this case, k minus is equal to j minus. So this would be the set j minus. This is the set k, and then the boundary here would be the set, this is set k plus, the boundary here would be j plus, and then j would be the intersection of j plus and j minus. Okay, so let me warn you against an assumption here. I remember giving my talks several times in the Graduate Center, and at some point, Dennis said, I always assumed that J minus was a lamination. There is no reason to think of J minus as a lamination, despite the picture. J minus is a set. In fact, Sullivan, I mean. In fact, Lubitsch has described J minus as a turbulation instead of a lamination, right? Because this set could be arbitrarily wild, and in fact, much of the analysis of Benedict's and Carlson strange attractors deals with the fact that this is an amazingly bad set, can be an amazingly bad set. Okay, so let me just say this is a turbulation. Okay, so there's no reason to think despite this picture, there's no reason to think in general, for a general parameter, that this is well behaved, or that J is well behaved either. Okay, so Hubbard also introduced functions g plus and minus of p. These are as the limit as n goes to infinity, 1 over 2 to the n log plus the norm of f to the n of p. Okay, so these are analogs in the two-variable setting of the function g of z equals limit n goes to infinity, 1 over 2 to the n log plus of f to the n of z. Yeah, thank you. So in this one, we've got plus or minus n. Good. This is, in the one variable setting, this is a green function, and this makes some kind of connection with potential theory. Okay, so, but another way of looking at these functions is if you, when Hubbard initially was drawing pictures, so what he would do would pick, say, a hyperbolic fixed point here, parameterize its unstable manifold by a copy of C. So we have some phi from C to C2 that's parameterizing an unstable manifold. And then inside this unstable manifold, you can draw the function. So this unstable manifold is inside J minus. And inside this, you can draw the function G plus, right, which gives you a nice computer picture. So you get something that looks kind of like a Julia set inside here. And then the level sets of the G plus function are nice regions. You get very nice pictures in this setting. Okay, so when, let's see. Right, so Hubbard in particular gave a version of this talk at the Graduate Center that I attended. He also gave a version of this talk in Orsay, which Smillie attended. And when Smillie looked at this setup, his mind immediately said to him, potential theory. In particular, he's thinking of a kind of a complex variable version of potential theory. And let me just, I think it's a very important tool. And let me just give you the introductory course on potential theory. Okay, so well, let me give you. Okay, so let's talk about. Let me just give you some examples of how potential theory works. Well, let's see. Now, what do I want to do here? Oh yeah. So So let me give you. If we describe potential theory in one variable. Okay, so we've got a Julia set and level curves of the, we've got this function g. G is the green function, so g determines a certain measure, equilibrium measure, or harmonic measure on the Julia set, and with that measure can be written as mu, and it's the Laplacian of g times dx wedge dy, where we want to interpret this in the language of distributions. Now, typically, if you think of potential theory as something that involves a metric, in order to talk about the Laplacian, you need a metric to make the Laplacian well defined. But the fact that we've got the Laplacian and this term makes this a holomorphically invariant object. So it's really something that's just dealing with the complex structure and not with the metric. So it's a very dynamically useful setup. And in fact, this measure is very important dynamically. Mu is an invariant measure, and mu is the unique. It's both. Well, it's the unique measure of maximal entropy. It also describes the distribution of periodic points for the map. So it's intimately connected with the dynamics of the map.
Be unique.
It's a measure of maximal entropy, and there is no other. Yeah. So it's very nice that it has this kind of independent potential theory description. Maybe it's in one variable, maybe it's something of a just an oddity. It's not essential to the theory, but we'll see in two variables this is a very a more important tool. Okay, so trivial examples here. If we look at f0 of z equals z squared, then our Julia set is just the circle, and g of z is equal to log plus of the absolute value of g. If we consider f sub minus 2 of z equals z squared minus 2, then our Julia set is the interval from minus 2 to 2. Instead of writing, let me not write down g of z, but what's useful, so following Hubbard's idea of taking this linearizing parameter, it's useful to look at pull back, consider the pullback of G with respect to the linearizing parameter. In this case, so the linearizing parameter takes Z to e to the Z, taking 0 to 0. So the inverse image of the Julia set is the imaginary axis here under the linearizing parameter, and the pullback of G is just, in this coordinate, is just the real part of Z, or it's the maximum of the real part of Z in 0. So level curves are like that. In this case, the linearizing parameter is Z goes to e to the Z plus e to the minus Z, and the pullback of the Julia set is just a half interval, and in this case, G of Z is equal to the real part of the square root of Z. Okay, so the level curves look like that, say. Okay, so yeah, so this in this, so okay. Now there's a connection. So one thing that the potential theory does is gives us a connection between growth rate and the geometry of the Julia set. Okay, so so G satisfies the equation G of f of Z is equal to 2 G of Z. So if you put that fact together, well, so if you know something about the growth rate, and with this equation, you also know something about the expansion. Okay, so in this example, the growth rate is linear. G is growing linearly, and that corresponds to having an expansion factor of precisely 2 at this fixed point. Okay, just because of this equation. In this case, the growth is like square root, and that corresponds to having an expansion factor here of exactly 4 instead of 2. Okay, so in general, the expansion of Green's functions is somehow related to the angle, this sort of angle of exposure. Here we see the angle of exposure is pi, and the multiplier, lambda, is 2. Here the sort of the angle of exposure is 2 pi, and the multiplier, lambda, is equal to 4. Okay, so in general, we get some connection between geometry and expansion, which is a useful thing in general. Okay. Let's see. So right. So then, in particular, it's the fact that the Lyapunov exponent of mu in this setting is greater than or equal to log 2, which means that from the point of view of the harmonic measure, on average, we're seeing a sector of angle pi. Okay? And that, in particular, that means that the harmonic measure puts very little measure inside fjords, right? I mean, you can have fjords where the angle is small, but those get relatively little measure, and the harmonic measure is concentrated out on tips where you're getting a larger angle. Okay, so in the one variable case, the fact that this measure is non-uniformly expanding gives you a kind of alternate way of seeing that expanding periodic points are dense in the Julia set. It gives you a method of seeing that without resorting to Montel's theorem. Okay, so that's useful in two variables where Montel's theorem doesn't hold. Okay, so let me, this was the one variable course, okay? We're ready to move on to the two variable course, okay? So this is the second semester of potential theory. Okay, so another way of seeing the complex invariance here is to write this expression as d dc of g, where this is the standard exterior derivative, and this is a version of the exterior derivative twisted by the complex structure. Okay? So these operators are operators on real-valued functions, but they're operators on real-valued functions that express the underlying conformal structure. Okay, this twisting expresses the underlying conformal structure. Okay, so so potential theory. Maybe I shouldn't write over. Maybe I'm okay. Oh, okay, you'll let me know. Okay, so potential theory. In two variables. Okay, so here we want to write mu plus and mu minus as d dc of g plus and g minus. Okay, so what do we get? In this setting here, we got a measure in our two variable settings. What we get is a current, whatever that is. So I want to what we get a current which should be thought of as a transverse measure. Okay, if you slice this, if you slice J minus, so let's look at mu minus. So mu minus will be supported on J minus. If you slice mu minus by a complex transversal, then you actually get a measure. Okay? So we should think of mu minus as a transverse measure, but we should not lose the thought that there is no lamination here, right? So let's keep both thoughts in mind at the same time. Somehow, this is a turbulation. We have no right to expect the existence. We don't know what a transverse measure is, but if we knew what it is, this would be it. Okay? So it's a nice thing that potential theory is doing for us. It's creating objects that should be dynamically significant in a setting where we're making no assumptions on the parameters. We're not picking parameters to make this set nice. We've got arbitrary parameters, yet we're still getting analogs of dynamically significant objects.
It lives on support.
It lives on its support. All right. Let me demonstrate my technique for solving questions in several complex variables.
Are restricting to the support?
Yeah, it's represented by negatives.
Okay, so just a comment here, as Lubitsch has pointed out to me, doing dynamics involves oftentimes, or in some cases, doing dynamics involves exploiting other fields in other areas of knowledge, and that's part of the interesting thing about dynamics. In this case, my exploitation of the theory of potential theory is via Bedford.
What did he say?
He said yes, I think. Between you and me, I think that's what we're going to get from this. Okay, so we define these so these things, whatever they are, they're giving a little additional structure to J plus and J minus, and we can also define, and they have nice multiplication properties, just like we had over there. Well, and these have nice multiplication properties. One of these expands by a factor 2, the other contracts by a factor 2. So if we look at this mu plus wedge mu minus, where again we have to be honest, we don't know what this means, right? If these were actual forms, we would know what this means, but I'm happy to write this. If I want to know what it means, I have to ask Bedford, right?
When you think of them as laminations, you understand. That's what it means.
Okay. Are you also willing to think of them as not laminations? Yes, no, if you think of them as laminations, we know exactly what this means. It's just like a Fubini kind of picture, okay? But well, maybe we're going to, on Sundays we'll think of them as laminations, some days we'll think of them as turbulations. Okay? So this turns out to be a measure of maximal entropy. Turns out to be a unique measure of maximal entropy. It's ergodic. It's invariant. It's ergodic. Again, it's amazing that we're getting this kind of nice dynamical object without any a priori assumptions on our parameters. So,
Didn't you say you don't know what that means?
the wedge?
Yes.
Yes. I said I don't know what this means. If these were smooth functions, I mean, if g plus and g minus were smooth, then these would be forms, and I could do this wedge of forms. But they're not smooth. I have to interpret this in more distributional language. So you're definitely moving into realms of analysis that are more subtle when you do that.
But he's asking, if you don't know what that means, how can you know it's a measure, let alone of maximal entropy? I think that's what is essential.
It's a paper.
Because they have Bedford.
Yeah.
I mean,
Sure.
you wedge differential forms, it has a geometric picture with the exterior algebra.
Yes.
And even when the picture, when they're non-transversal, you get 0, and most generically, or probability 1 is transversal. So you can imagine there would be an analysis where with probability 1, they are transversal, and it doesn't mean a geometric intersection. You just have to sort of analyze it.
Yes. You could, right.
Lamination picture almost everywhere.
Yes. That's an insightful comment, and it's true, and it's almost everywhere with respect to this measure mu. So it's a little bit circular, but it's true. But yeah. So but keeping that picture in mind, we can look at this. We can look at the support of mu. Now this will be contained in the intersection of the support of mu plus and the support of mu minus. So it will be contained inside J. But if you keep Dennis's picture in mind, it should be measuring not just the intersection of these sets, but the places where these sets are intersecting transversely, right? So, and let's call this, define this set to be J star, okay? So this is the set of transverse intersections, and then we have J star contained in J, and so Bedford, Lubitsch, and S showed that the hyperbolic periodic points of this map are all contained in the set J star, and in fact they're dense in the set J star, and in fact mu describes the distribution of periodic points in this 2-variable setting, just as it does in the 1-variable setting. Okay, so right, so right, so we have J star contained in J, and so these are both. I mean, this is so we did sort of the extension to 2 variables of this 1-variable picture. So let me I'll summarize here. Extension of the one variable picture. Okay. So this, in some ways, this completes the set of significant sets. Let me add this one that wasn't on Hubbard's original list as also important set. In fact, both J and J star are very natural analogs of the Julia set in one variable. You can think of the Julia set in one variable as the boundary of the boundary of K. Or you can think of the Julia set in one variable as the Shilov boundary of K, a kind of a functional analytic boundary. You can think of it either way. In two variables, J star is the Shilov boundary of K also, right? So in that language, it's a very direct generalization of the Julia set in one variable.
Is the closed support of mu?
The support means the closed support of mu?
Yeah, support in the standard sense.
It's not really a set.
Yeah. Okay, so let's see. So returning to historical discussion here. Smillie heard Hubbard speak in Orsay, and while he may have been impressed with using G+ to draw these pictures, he said, what's really going on is this potential theory point of view. So Bedford was visiting Smillie a short time later, maybe in the summer in Orsay, and Smillie said, well, let's think about this complex Hénon map. Hubbard has just introduced this, but you and I know what's really going on. Let's prove something. Okay, so I looked at this complex Hénon map, and I was about to go to Cornell, so I thought, well, this is probably a good thing for me to think about, and from the dynamical systems point of view, but I should have at least I have something to talk about with my in Ithaca. Okay, and then a year later, Hubbard had a conference at Cornell on complex dynamics, where this newly introduced Hénon map was a character, was figuring. In his, so at that conference, I met Bedford again after not seeing him for many years. And I said, well, what have you been up to? And he said, you wouldn't believe it, it's so stupid. And I said, oh yeah, I have the same story. And he says, well, I've been thinking about the complex Hénon map. And I've just been getting nowhere. And I said, oh yeah, I've been thinking about the complex Hénon map too. I've been getting nowhere. So we decided at that point that we should probably work together. At least we could support each other in our lack of progress. But yeah, okay.
Which year are you going?
So this would be, I think it's 1987. Does that sound right? Okay. 1980s. Okay. So at that conference, Hubbard explained some of what he had learned about the complex Hénon map. In particular, one of the things he said was he knew that the hyperbolic periodic points were dense in J, but he didn't quite say that. He said, if the hyperbolic periodic points are not dense in J, then everything I know is wrong. Okay, so we later interpreted that as saying that the equality of J star in J is the Hubbard conjecture, but that doesn't quite capture the nuances, right? So so it may be that yeah.
I just assumed it was true.
Right, right. Well, I think it's amply. I mean, I'm assuming that part of your. I mean, you had lots of evidence because you were looking at lots of computer pictures, right? And yeah. So we still don't know. I mean, maybe it is true. And I guess if it's not true, then we can go back to you and say, well, everything you know is wrong. But until that point, we have to admit that maybe you know some things that are correct. I know, but it's okay. Okay. What do I want? Let's see. Okay, so in 1987, Friedland and Milner published a very elegant paper on the general structure, the algebraic structure of automorphisms, of polynomial automorphisms of C2 and R2, which kind of put this complex Hénon map in a more general setting, but it still meant it was a good thing to study. I mean, it's kind of central to the general polynomial automorphisms. Okay, so after...
John?
Yeah.
Just generally reason why people don't work on this Jacobi problem using dynamics.
Jacobian conjecture?
Jacobian conjecture?
Yeah.
Because there's so much else to do. Life is short.
Jacobian conjecture
Is what?
Poison.
Yeah. Yeah. I mean,
and the answer is yes or no, so
yeah. Right.
Everybody wasted so much time.
Well, think about Hubbard's question of understand the combinatorial structure of the parameter space. That's a rich question where, undoubtedly there's lots to say. It's not yes or no, right? So it's more fun to think about that than the Jacobian conjecture. Okay. So then Bedford and I did start working on this, and then when we had challenging issues, we had to bring in Lubitsch to help us through those. And then, Forness and Smillie were also, continued working. I mean, I guess Forness joined in with, Smillie joined in with Forness, and they were very interested in this kind of facts about describing potential function. Harmonic measures describing distributions of periodic points, but they went on to look at that in other contexts, higher dimensions, various other settings. So Bedford and I had the sense that there were lots of interesting questions remaining in the two-variable setting. On the other hand, Forness and Smillie were pretty sure that the two-variable setting was of no further interest, so they were off in higher dimensions. And Hubbard kept reminding us, or kept reminding me occasionally that we hadn't actually started on the interesting questions, right? We were still, I have to admit that he was right, but so we were somehow in the middle here, doing our thing, but with not much respect from either side somehow. Okay. Well, so we wanted to somehow both apply potential theory to some question, but address maybe deeper questions that are dependent on the parameters, right? I mean, in dynamics, it's a mixed blessing to have some theory that makes all parameters look the same. You want to say, why are some parameters different from others? In particular, it's interesting to look at the hyperbolic parameters, where J plus and J minus might actually be laminated. So the problem that we chose to look at was the question of real maps, where take the parameters to be real, but you assume that the entropy is maximal. Okay, so the entropy of the complex map is always log 2. The entropy of the real map can vary between 0 and log 2. And we want to look at the situation where the entropy was log 2. Now, from the dynamical point of view, again, I think people in dynamical systems said, well, we kind of understand this. We know what's going on. But from the potential theory point of view, it's a very nice setting because there's a very nice connection between the potential theory point of view and reality here, in this particular case of maximal entropy. Okay, so that's, maybe I should write something down. So let's see. So let's assume parameters are real. And let's also assume that the topological entropy of F, and let me write F sub r for the restriction of F to the real to R2 equals log 2. Okay? So from our point of view, this did allow us to distinguish in some way between why are some parameters different from other parameters in the potential theory perspective. Well, what we discovered is that, well, so in this setting, because there's a unique maximal entropy, a unique measure of maximal entropy, and because so we know in fact that there's a real measure of maximal entropy just by general principles. There exists some real measure of maximal entropy. Well, it must be that this mu that we've constructed, the mu that we've constructed must be the real measure of maximal entropy. So the support of mu must be contained in R2, which is a powerful tool. It gives you lots of information about what's going on here. Maybe I should let me just, if we look at the one variable setting, we go back and I don't know if it's still, yeah, if we look at the one variable setting, then to say that the Julia set, which is a priori a subset of C, is actually real. Well, one of the examples here would be this Chebyshev example. Okay? And what happens in this Chebyshev example? Well, it's actually semi-conjugate to the doubling map on the circle. So if you look at any periodic point, the multiplier of that periodic point will be 2 to the period. Okay, so it's got uniform expansion, except that this point over here is exceptional from that point of view. Right? At this point, we saw the multiplier is 4. Right? So what happens in this setting is there's a fixed point with multiplier 4, and then outside of that fixed point, there's a uniformly expanding metric. Okay? And it turns out that picture basically holds for all of these maximal entropy values. That there's and in fact, just making this assumption, a whole very interesting structure arises. Arises out of these kind of abstract assumptions. We can see that, and it tells us that in this setting, either the map is a horseshoe, which is to say uniformly hyperbolic, or there is a one-sided periodic point, and there's a homoclinic tangency, quadratic homoclinic tangency of the stable and unstable manifolds at that one-sided periodic point. Okay, so it all comes out of this reality of J, even the quadraticness of the tangency. Okay, so using these, why is this nice? Well, it's partly partly nice because in the two-variable setting, it's very hard to get your hands on behavior of maps in general, as opposed to the one-variable setting where everything comes down to behavior of the critical point. Right? Yeah?
Do you know that J equals J star in this case?
We know that J is equal to J star in this case. Yes. That's by using potential theory, by asking Bedford. Yeah.
And do you know exactly which real parameters satisfy these conditions?
That's a good question. So this, in some sense, well, let me. I'm about to answer that question. So I just want to say it's a hard question first of all before I answer the question. So it's a hard question because in two variables, there is. In one variable there's a critical point. You know what happens at the critical point. You know the dynamics. In two variables, it's a diffeomorphism. There are no critical points, right? What are you going to do to actually analyze this? Well, we do show that if it's on the boundary of maximal entropy, then there must be a tangency. So that's something you can look for. Okay, but so if you combine the kind of the theoretical picture with a lot of very deep computer ideas, you get the work of Zen Arai and Yutaka Ishii. How many eyes? And 2 eyes. Thank you. I know the answer. 3 eyes. 2 eyes total? Okay. Sorry. So in this work, they nailed down precisely. Let me just schematic here. They nailed down precisely the set of parameters for which you have maximal entropy. So there's this tangency line, and they show that this is exactly the boundary of so entropy is h equals log 2. To the right, it's the entropy is continuous in this setting, so entropy is log 2 on the boundary, and then it drops when you cross the line. Okay? And I flipped it, yeah. Okay, so right. So actually, our approach to this this setting, well, so we wanted to turn this example into a theory. So so this is a beautiful example, but yeah. So we wanted to promote this. And let's see, the key word here is quasi-hyperbolicity. Okay, so we wanted to invent a theory of quasi-hyperbolicity. And before I tell you the definition, let me just say that this is a key example of quasi-hyperbolic maps, as are genuinely hyperbolic maps. So this is some extension of the notion of hyperbolic. And we can think of this as a two-variable analog of Mizarevich parameter values. Where by Mizarevich, I don't mean that the critical point is pre-periodic. I mean it's non-recurrent, right? So it could have an infinite orbit. Okay, so it's a two-variable analog of the Mizarevich parameter values, and it, in some sense, it addresses the turbulation question. Okay, so it tells us. It tells us when J plus and J minus are actually filled with manifolds, as opposed to containing lots of manifolds and who knows what else. Okay, so my time is short. I won't tell you the definition of quasi-hyperbolicity, but it's just what it's supposed to do. So let me say also conjecturally. So this is equivalent to a John condition in slices. Okay, so it's something, I mean, so let me not say what that is, but that in particular, it's something that Hubbard could see from his pictures. I mean, you take a slice, you look at it, you look at the geometry of the K plus inside the slice. If it satisfies a John condition, then you're on your way to being quasi-hyperbolic. Yeah.
Which some of the parameters that he considered are hyperbolic for the one-dimensional. Do you have hyperbolic maps among your?
Yes. This family includes all hyperbolic maps. Okay, and basically the way we approach it is we say, assume that there's bounded folding of unstable manifolds. Okay, if there's bounded folding, then you've got this nice structure, including these complete analog of this Chebyshev parameter. We have a finite filtration of J, so that on the difference between successive levels, we have uniformly expanding metrics. And we use G plus and G minus to construct those. Okay, so in the last 2 minutes, let me say that Bedford and I have returned to looking at, well, so this conference is an example of something that I haven't seen for a long, just recently there've been a small number of conferences in which there's been more than one talk on complex Hénon map. This is an example of such a conference, and I'm very pleased to attend such conferences. I mean, for a long time I would, there'd be 0 or 1. And it's because I think there's something of a resurgence of interest and ideas in this field. In particular, there's a new, relatively recent work of, recent work of Lubitsch and Peters and Lubitsch and Dujardin, which has lots of new ideas. And in looking at this work, Eric and I were saying, well, some of these new ideas might go back and help us solve problems that we were stuck with back in the day when we were trying to think about, in particular, quasi-hyperbolicity. So let me just give you two up-to-date theorems. If f is quasi-hyperbolic and there are no tangencies, of stable and unstable manifolds. No. If it's quasi-hyperbolic, there's stable and unstable manifolds through every point. So I'm allow those stable and unstable manifolds. Then f is hyperbolic. Okay, so it's useful. This means this theory of quasi-hyperbolicity gives us an actual test for hyperbolicity. This is the kind of thing that Romain was using in his talk when he was talking. I mean, the relationship between hyperbolicity and structural stability, very interesting question. And this is this is something in that direction. And then let me give you a second theorem. So in our definition of quasi-hyperbolicity, we it's kind of annoying, but we assume that J is equal to J star. It's annoying. Well, in our example, we don't have to do that. In the real maximal entropy, we know it's true. But our technique is to build from the periodic points. So we're building some kind of structure on J star, and we don't know that J star is equal to J. So it would be nice to not have that assumption. It would be convenient. And we were encouraged by a paper of Forness where he proves that if you assume that the map is hyperbolic on J star, then he asserts that J is equal to J star, right? Which suggests, that seems to be, that takes care of that technical detail, right? Because what we were figuring, we can extend that result. Unfortunately, it took us a long time to read Forness's paper, and when we actually got all the way through it, it turns out it's not correct. The proof is wrong. The proof is in two parts. Part A, part B. Both part A and part B are wrong. But interesting ideas in the paper, and combining the inspiration from Forness with some technical ideas from Lubitsch and collaborators, we can show that if F is QH on J star, which is, that's how so let's not assume that J is equal to J star. Let's assume it's quasi-hyperbolic on J star, and the Jacobian parameter value is less than 1/2, then then J is equal to J star. One-fourth would be the classic. One-fourth would be moderately dissipative. I think in our case we can actually, in our case we can actually do 1/2. So that's really moderately, just barely dissipative. Okay, and maybe I'll stop that.
Questions?
Can you give us some idea of what quasi-hyperbolic means?
Yeah, so it's absolutely. It's bounded folding, which means that what do I want to assume? If there exists epsilon greater than 0 and constant c, so that then let me draw you a picture, so that for any hyperbolic parameter value, this is, so I'll talk about quasi-expanding. If we look at the unstable manifold so if this is our point P, and this is the ball of radius epsilon around P, if we look at the component of the unstable manifold that lies inside this ball, then the area is less than C. Okay, so it's a bound on sort of the local area of unstable manifolds. Yes. So if we so this is the unstable. We're looking at the unstable manifold of P intersect the ball on epsilon sub P, and then we're looking at the component of P inside this set. Okay, so that's what's drawn in orange. Okay, and we want a uniform bound over all hyperbolic periodic points for the areas of such things. Okay, so this is a minimal kind of thing you would want if you think that J minus, in order for J minus to be kind of laminated and not turbulated, right? If you've got unbounded area, then you'd really have to say that J minus is kind of a mess. Okay, so if this condition holds, then we say that the map is quasi-expanding. If the same condition holds for stable manifolds, we say it's quasi-contracting. If it's quasi-expanding and quasi-contracting, and if J is equal to J star, then we say it's quasi-hyperbolic. Okay? Yeah.
For one epsilon, is it true for all smaller epsilons by
Yeah. Yeah.
Oh, yeah.
I have, it's a comment on ancient history.
Good.
The reason I started studying Hénon maps,
Yeah.
because Calabi at a tea before a colloquium in Paris, said, you know how to make all these computer pictures. Why don't we make a nice computer picture of the Fatou Lieberbach set so that we can finally understand what these things really look like. And that was the origin of all of my study of Hénon maps. It comes from Calabi's question of trying to understand what the boundaries of Fatou Lieberbach sets look like.
Well, that's a good pedigree, right? I mean, if we think of this as descended from Calabi, yeah. And so the connection here is that basins of sinks are Fatou Lieberbach domains in this setting, which is to say they're bihomomorphically equivalent to C2, yet they're proper subsets of C2, right? And that was, yeah.
I did not actually focus on the actual example given by Lieberbach, but
Yeah.
Sandra Hayes here has studied it extensively.
Yeah.
Thank you.
If there are no more questions, well, thanks again.